we were wrapping up aromaticity and looking at aromatics and recognizing that not all aromatics look the same. Some aromatics have nitrogens, some aromatics have oxygens. Some nitrogens don't contribute a lone pair, some nitrogens do contribute a lone pair. Some oxygens contribute one lone pair, some oxygens don't contribute any lone pairs. No oxygen ever contributes both lone pairs. Oops. So when you look at adenine, aromatic or anti-aromatic or non-aromatic, how do we decide? And also, do you guys know what adenine is? It's part of DNA. What do they call that?
Nucleic acid. Yeah.
Not a nucleic acid. A nucleotide?
Yeah.
There's a difference between a nucleotide and a nucleoside. I don't know what it is. Is it a nucleic acid? I don't think so. Okay, so how do we analyze it? First of all, it's a bicyclic structure. So, do I analyze one ring at a time? Do I only analyze one ring? Or do I have to analyze both rings together? What do you remember from yesterday? Sorry, Mimi?
No.
You remember nothing from yesterday. Okay, good start. Yeah, if both rings are fully conjugated and fused like this, you have to consider both of them together. But if one, even if they're fused, if one ring lacks any amount of conjugation, that entire ring is just ignored. Anything that's a part of it. We only count pi electrons, and you remember this from the carbonyls that we talked about yesterday as well. We only count pi electrons that are held within a ring. We don't count electrons that maybe would be outside of a ring. And if a side ring is not fully conjugated, we wouldn't count any of those electrons either. Only electrons inside of the ring or rings that we're analyzing. So the question is adenine fully conjugated? Are both rings fully conjugated? Well, there should be a specific atom that draws your attention. What atom should we look at to try and answer, is it fully conjugated, is it not?
The nitrogen on the bottom.
Yeah, the nitrogen on the bottom left. Because all of the other carbons and nitrogens, excluding the one we don't care about out of the ring, are obviously sp2. And we know that they're obviously sp2 because they are clearly shown in pi bonding. So has a pi bond, has a pi bond, has a pi bond, sp2. But this nitrogen down here has a lone pair that makes us wonder, is it sp3? Does it hold that electron pair to itself in a hybridized orbital? Or does it conjugate and share that electron with the rest of the ring? So the question is, if it's sp3, what is the marcation of the molecule? Well, if that nitrogen is sp3, then we do not consider anything on the left-hand side, and we would only analyze the right-hand side of the molecule, which has the same shape as pyridine, the same shape as benzene, just has an extra nitrogen. So it's aromatic. 2, 4, 6 pi electrons. But if nitrogen is sp2, then both rings are fully conjugated, and the pi electron count climbs 2, 4, 6, 8, 10. I'm going to circle all of those pi electrons, including the lone pair. And 10 pi electrons means that the whole structure is aromatic. So is there any difference between part of the structure being aromatic versus the whole structure being aromatic? This is different than those examples we did yesterday where it's either just a non-aromatic structure or an aromatic structure and it's lower in stability. Sorry, it's more stable. Now we're actually looking at part of the structure is non-aromatic while the rest of it is aromatic versus the whole thing. What do you think is better energetically for this molecule? What will that nitrogen on the bottom left energetically prefer to do? Make the whole thing aromatic. Evan, what do you think?
Yeah, I'd say as an sp2.
Make the whole thing aromatic rather than just part. Jew? Mimi? So we have a preference not just for partial. Jordan, what do you think?
I also think it's going to be sp2.
Not just partial aromaticity, but full aromaticity, maximize aromaticity. Great, I agree. There's a structure I didn't put on here. I kind of wish I had. Caffeine is a very interesting molecule to consider because caffeine has this structure, and these are actually methyl groups. It has this structure that does not scream aromatic, except for maybe on the right-hand side where we can see this nitrogen is in the same environment as up above. It could be sp3, but if it's sp2, this ring on the right is definitely an aromatic ring. But we can do something with these carbonyl groups. We can draw a resonance form from the amide. This is maybe not the best resonance form because it maximizes charges. But what we see when we draw this resonance form is that we also maximize aromaticity. Now that structure on the left looks a lot like an aromatic ring. And so maybe caffeine has some intrinsic aromatic properties because one of its resonance forms is the true definition of an aromatic structure. Is this the best resonance form? I actually don't know. I haven't found the answer to that before. Whether this represents a better picture of what the molecule actually looks like or not. Because it does break our rule of not minimizing charges. But aromaticity already breaks rules, like not taking the highest hybridization state possible. Okay, proline, an amino acid, aromatic, anti-aromatic, or non-aromatic? Mimi?
I'm just guessing no.
Why are you guessing that?
Well, I'm saying because I don't really see like the double bonds a lot, except for like on oxygen, but I don't understand how that can be.
Okay, so let's follow Huckel's rules. Is the structure cyclic? Well, you were mentioning the double bond on oxygen, and this is the only part of the structure that's cyclic. So this would be the only part that we should even investigate for aromaticity. Is the aromatic, is it cyclic? Yes. Is it planar? Probably not. because of the third reason, which is it fully conjugated? All of those atoms are sp3. This nitrogen is one that we would typically look at and say is sp3. So why am I not giving this option anymore? If it's sp3, it's one thing. If it's sp2, it's another. I'm not even going to consider that this nitrogen could be sp2. sp2 hybridization allows a lone pair to become part of a pi system. Putting this lone pair into a p orbital, there's no pi system for it to join, right? There's no benefit from this lone pair having more electron repulsion and shorter angles between all of the electron regions. There's no benefit to that being in a p orbital. So it's only going to benefit from having the greatest bond angles and the least repulsion, sp3. So it is not planar, it's not fully conjugated, it is non-aromatic. Even if you just looked at this carbon and said, that's sp3, non-aromatic. But also, all of the carbons are sp3, and so all of the nitrogens. The nitrogen is also sp3. What about histidine? Does histidine have aromatic character, anti-aromatic character, non-aromatic character? It has aromatic character. Now, I think we can also say that histidine has non-aromatic character as well, right? It's got this chain that is like very much non-aromatic, but it definitely has aromatic character. That's a really funky looking 5-membered ring. Something looks really off about it. Still doesn't look great, but very clearly 4 pi electrons, and the nitrogen is the only one that we have to rationalize. If the nitrogen is sp2, aromatic. So it will be sp2. How about these anthocyanins? I'm going to abbreviate this structure just a little bit. I'm not going to draw all of the groups coming off of it. So just taking this part, does this have aromatic character, anti-aromatic character, or non-aromatic character? Well, it's a bicyclic, so we need to look at both rings and decide, do we count both rings together, or is one of them ineligible? Every atom is sp2 hybridized. No questions about it, right? This oxygen is clearly in a pi bond, so it's fully conjugated. So now we just count the pi electrons, 2, 4, 6, 8, 10. 10 pi electrons follows 4n plus 2, but what about this lone pair that oxygen still has? Is that lone pair included? Kind of like nitrogens? Do I need to count the lone pair from this O? Why not, Ju? Right. It's already aromatic, so that lone pair is not going to improve aromaticity. It's a localized lone pair. Here's another way to look at it. If an atom is not in pi bonding explicitly, then it has the potential to be in pi bonding according to these secret rules of aromaticity. Like this nitrogen can share its lone pair to make it aromatic because it doesn't already have its p orbital consumed. But these nitrogens that are already sp2, already in a pi bond, cannot share their electrons. Their lone pairs have to be localized. Oxygen, for the same reason here, cannot share its electrons. Those electrons are localized because its p orbital is already consumed. Jordan was asking this morning, and the reminder is that we know that oxygen has a p orbital being used for this pi bond, if we were to try and put a second p orbital for this lone pair, all p orbitals are perpendicular to each other. So if this p orbital in the pi bond is already in phase with all of the other p orbitals of the aromatic ring, then the other p orbital, just to stick the lone pair in, would be perpendicular and wouldn't conjugate. It wouldn't overlap. So even if you could, it wouldn't improve anything. Tryptophan. I'll let you guys take it from here. Aromatic character, anti-aromatic character, non-aromatic. Jordan? Do you guys agree? Do you see how tryptophan looks like benzene, plus it looks like that histidine ring? And we know that benzene is aromatic, and we know the histidine ring is aromatic. Good morning. So if I take two things that I know to be aromatic, fuse them together, it should be aromatic. Pyrrolysine. This long one. Jaylee? Non-aromatic. There's only one ring, and that ring is, yeah, it's not fully conjugated. It's got 3 sp3 carbons in it, so there cannot be an aromatic pi system. How about oxidiazole? Which is such a cool structure in my opinion. Oh, I did that wrong. Do you guys remember furane from yesterday? By the way, if you add 4 hydrogens, you get tetrahydrofurane, which is THF. So if you've ever used THF or seen it on your reactions as a solvent, this is its big brother, furane. We looked at furane yesterday, and we said that furane will keep one of its lone pairs in a p orbital so that it has a full pi system. And one of its p orbitals sits in a hybridized orbital, the same type of hybridized orbital used to make all of its sigma bonding. A delocalized lone pair and a localized lone pair. What about in oxidiazole? Oxidiazole. Has anything changed between furane and oxidiazole? It's essentially the same. Some of the carbons have been swapped out for nitrogens, but those nitrogens are the same hybridization as the carbons. So it is essentially the same. One lone pair delocalizes, one lone pair localizes, and the lone pairs on nitrogen, localized lone pairs or delocalized lone pairs? Localized to the nitrogens. They cannot be delocalized because the nitrogens are already part of the delocalized pi system. They already have their pi bonding. Man, I remember trying to explain this to a friend of mine in college. It can be tough. My first time out of OCHEM 2 trying to tutor this topic, you have to have a grasp on hybridization, what those orbitals are. You have to have a grasp on their geometry, knowing that p orbitals are perpendicular. It can be challenging. But orbitals are really a lot simpler than you think. They're just math equations. And there's so few combinations of math equations. Once you know what possibilities there are, you see these nitrogens, and you know that it's got sp2 orbitals, sp2, sp2, sp2. So aromatic, and then methyl imidazole on the bottom right. Aromatic. I think we went through that one together. All right. So this idea that we've had of if something can conjugate, then it does conjugate. If it can become part of an aromatic system, then it wants to become part of an aromatic system. This actually we find to be true for a lot of other groups as well. First, consider metabromotoluene.
Sorry, could you give me a reminder of the difference between like anti-aromatic and non-aromatic?
I would love to, but I'd love to give your classmates a chance to answer that instead. The difference between aromatic and anti-aromatic. There might be different ways of approaching this, so take that how you may.
I see it as anti-aromatic, you have to follow some of the alcohol rule, like the planar, another one.
So you still have to follow cyclic, planar, and fully conjugated, whether you're finding a molecule to be aromatic or anti-aromatic. Salsabil.
Isn't the main difference the equations from 4n equals pi?
The main difference is the number of pi electrons and the equation that helps you determine which one it follows. 4n tells us
It's
anti-aromatic. 4n plus 2, aromatic. Anything else to add to that?
Anti-aromatic is less stable than non-aromatic?
Is not just less stable, because so is non-aromatic. Non-aromatic is less stable than aromatic. Anti-aromatic is like equal and opposite in its stabilizing force. I guess I didn't really talk about this because there aren't a lot of anti-aromatic compounds, but anti-aromatic compounds work so hard not to be anti-aromatic. If we look at cyclobutadiene, cyclic, planar, fully conjugated, 4n pi electrons, anti-aromatic. Cyclobutadiene exists, and it actually doesn't exist as an anti-aromatic system. What it does is it stretches out along its sigma bonds so that the p orbitals on one side can't overlap with the p orbitals on the other side. It elongates its bonds to break conjugation. So if I gave a problem like this, I have to give those prefaces like assume it's cyclic, planar, and fully conjugated. Assume it's not doing anything to break its aromaticity. We saw cyclooctatetraene does the same thing. Cyclooctatetraene bows up so that its p orbitals can't conjugate. It does anything it can to break anti-aromaticity. We saw the same thing with quinone. We saw how quinone should, in theory, be able to be fully conjugated, but would become an anti-aromatic system if it did, so it just doesn't fully conjugate. The lowest energy system is not a fully conjugated system. So a lot of structures do everything in their power to avoid being anti-aromatic because it's that destabilizing. It's better to be non-aromatic than anti. There's one last thing I was hoping you guys would touch on about the difference between aromatic and anti-aromatic. Comes from the Frost circles, the MO diagrams. Yep. Anti-aromatic has radicals. Aromatic does not. When you look at cyclobutadiene with those 4 electrons, 2 unpaired radicals, that's part of the destabilizing factor. Was that helpful? Great. Good work, guys. Metabromotoluene has these 2 groups, bromine and methyl. And these groups aren't really good at engaging in conjugation with the aromatic ring. The methyl group is considered an electron donating group. It has low electronegativity, but it has a lot of electron density, and so that electron density can get pulled towards the ring. This is called hyperconjugation, where a bonding orbital overlaps with a p orbital in part. But there's not great orbital symmetry between bonding and p orbitals. So it can kind of push its electron density in, but not very well. Whereas the bromine is an interesting case. The halogens are an interesting case. We know that halogens have a strong dipole away from carbon, but those halogens also have 3 lone pairs, and if that halogen placed one of its lone pairs into a p orbital, then it could have conjugation with the ring. It's outside of the ring, so we're not saying that this is impacting its aromatic character, but we're just saying that if the ring asked for any electrons, bromine could push electrons in by having a p orbital already adjacent to it. So within rings, atoms like to conjugate with the aromatic system. Even outside of the rings, atoms like to conjugate with the aromatic system. So let's look at that structure on the top right where we have 2 nitrogen groups. One is a nitro, NO2, and one is an amine. One of these groups we consider electron withdrawing when it conjugates. Remember, conjugation is an uninterrupted series of p orbitals. So wherever you find a p orbital next to any other set of p orbitals, they're conjugated. And if an atom can conjugate, it prefers to conjugate. So this nitrogen is involved in a pi bond adjacent to the pi bonding of the aromatic ring. This nitro group is conjugated. It's conjugated to the ring, meaning that their pi systems are allowed to interact. This nitrogen looks like an sp3 nitrogen, 4 electron regions. But if it holds its lone pair in a p orbital, sp2, then it can be conjugated, and it prefers to conjugate. So let's look at what that looks like. Nitrogen can push a lone pair into the ring. Okay, this is a resonance form, which means that lone pair is pi electrons. Because resonance only moves pi electrons. And if these are pi electrons, then they must be in a p orbital, right? And if they're in a p orbital, then the nitrogen must be sp2 with its one remaining p orbital left over. So nitrogen pushes electrons in. My aromatic ring will need to shift its pi electrons around. The aromatic ring can actually start shifting pi electrons out of the ring because it's conjugated to this nitro group, and the nitro group can push electrons onto the oxygen. So one group, nitro, pulls electrons out. One group, the amine, pushes electrons in. That gives us electron donating groups and electron withdrawing groups from the ring, relative to the ring. Have you guys drawn the nitro structure before? This is often abbreviated as NO2, but I need you to know what it looks like because we're going to be doing a lot of these resonance forms in our worksheet today. NO2 is a Zwitter ion. You guys heard that term before? It means that it's neutral, but it has both positive and negative charges. You can't tell that it has a positive and negative charge until you draw it out, and then you see a single bonded O, negative charged. A tetra bonded nitrogen, positively charged. And even in this new resonance form, the nitrogen is still positively charged, but the oxygens now both hold negative charges. Remember we talked about resonance last week, and we were looking for these 3 atom systems. Nitrogen has a lone pair and then a pi bond. And then this carbon is going to need to use electrons, 1, 2, 3. This carbon is going to need to use electrons, 1, 2, 3. So there's a series of 3 atom systems all the way through this ring to get us to this next resonance form. Electron donating, we'll call these EDGs, and we're going to review more of these next week as well. Electron withdrawing. Can I have you guys draw the arrows on this next structure to go from the resonance form on the left to the resonance form on the right? And then can you identify which connection to the aromatic ring was an electron donating group and which connection was an electron withdrawing group? Working on your arrows?
Yeah.
Nice. Perfect. Perfect.
Sorry, there's so much writing on my paper.
Going the wrong way.
Wrong way?
Yeah, you're giving.
Oh, so you would give up an electron here, dumping this way. And
Well,
then
think about it this way. You're giving electrons to O, and O already has an octet.
Oh, yeah. But then that does become positive.
Right.
Sorry.
Right. So your resonance. Oh, of course.
I couldn't see it, so I was like.
Oh, yeah.
That's why.
Absolutely. Giving electrons to oxygen, who already has an octet. When a bond breaks, does it break toward the more electronegative atom or away from the more electronegative atom? Yeah. So when you broke that CO pi bond, and you broke the CO pi bond away from O, that's your first indicator that something's wrong. And when a bond forms, does it form from the more electronegative atom or from the less electronegative atom? This one feels a little counterintuitive, but it's always from the more electronegative atom. The atom that owns electrons gets to control when they are taken and shared. So pushing from O or towards O. That one is going to break the octet on that oxygen because it already has 8. Perfect.
So, when we're doing like these ones though, how come we're not like pushing electrons just because it doesn't need to because there's not those pi bonds that connect to those atoms?
We can push them. Here's histidine. Well, I don't know. I think there's an R group here. I can push these electrons. It just isn't necessarily the major resonance form because it's going to create a negative charge and a positive charge in my structure.
Right. Is that what we're doing with this?
But that doesn't, well, yes, it is. And it's going to segue into what we do today.
Okay.
So what I was introducing you to was that in an aromatic ring, hybridization is not what you think. outside of an aromatic ring, hybridization is not what you think. Or adjacent to the aromatic ring, hybridization is not what you think either. So this was all kind of a segue around how hybridization regarding aromatic rings, hybridization and conjugation are impacted both within an aromatic ring, and outside an aromatic ring. So this is just to demonstrate that things in and out of the ring can actually push and pull electrons from the ring. And even within a ring, electrons can move around. Not that that necessarily is the most useful. I mean, I will say this. If we were in a more advanced organic chemistry course, we can show reactions that happen from aromatic rings like this. And we can use the resonance to demonstrate this carbon has a partial negative because of nitrogen's delocalized lone pair. And carbon, if it has a negative, is more likely to use it than nitrogen. We're just not going to do that. Okay, I think I had two more that I wanted to look at. We're going the wrong way with the electrons. When a CO bond breaks, that bond should break towards the more electronegative atom. So how does oxygen get the negative? It took its electrons back. Actually, if you were pushing electrons the other way, this oxygen would become a 2+, I believe. Maybe a 1+. From this oxygen on top. So when you break a bond toward the more electronegative atom. It owns the electrons. When you form a bond, like with the oxygen on top, the electrons come from the more electronegative atom. And then we can kind of see what needs to happen within the ring. Each of the pi electrons needs to shift around. That's a lot of arrows in that ring. And I'll tell you something, it doesn't have to be. I'm going to redraw this starting structure, but I'm going to redraw it with the other resonance form of benzene. Because remember, benzene doesn't have the pi bonds in one spot or the other. Benzene really has a 1.5 bond everywhere. So the difference here is simply the placement of the pi electrons in the ring. Now look at how many arrows I need. Oxygen, pi bond, oxygen. I cut out 2 electron arrows because I didn't have to mess with the pi bonds in the ring. They were already where I wanted them. So which one is accurate? Is the arrow pushing on top more accurate to get that product, or is the arrow pushing on bottom more accurate to get that product? Both are perfectly illegal. I mean, legal. Both mean nothing to the structure because these are just our silly little ways of representing a very complex thing. What's the hybridization of this oxygen? Think about it. Don't answer just yet. Keep holding it. What's the hybridization of this O? Come up with a rationale. Talk to each other. Convince each other of the hybridization. We only move on once it's unanimous.
Wait, so what do you think it is? Do you think it's SP3?
It's gonna go with SP2 as well.
Oh, okay.
Are you succumbing to peer pressure? Because if that's the case, I'm going to make you answer the.
Thank you.
You're welcome. Of course.
But then if you look at the, oh, never mind, it wouldn't matter. Then this side can't be aromatic anyway. So you don't even count this one anymore. So, I think that's
What? A trick? I don't ask trick questions. What is a trick question, by the way? Maybe I do, and I just don't know that I do. A trick question is one that
well, when you
tempts
asked,
your intuition.
what did you ask just 2 seconds ago? Oh, which one's more right?
Yeah, okay. That is a trick question. That's a trick question because the answer was neither of them are better than the other. That's fair.
But I feel like usually you don't.
I don't grade on trick questions. That's a bad thing to do.
Wait, what do you think?
I think SB2.
What do you think that? Well, I'm just saying if it's gonna have a pipe on, it has to have a the orbital. So therefore, it has to have
I run so much on SB. I'm like struggling to even figure out my own notes. I'm like, what was I writing in here?
I hate that.
I'm like,
Yeah, I think one thing about these worksheets is that it kind of incentivizes you to take all the notes on the worksheet, and then it can feel harder to follow. Instead of like taking notes in a notebook and then having the worksheet adjacent to it. But there's a lot of notes that I put relative to a molecule, so then you'd have to redraw the entire structure. And maybe that's something to do after class, is to take the worksheets where you took all these notes and then copy them into a notebook to reiterate, clarify, give more examples. I know that takes time, right? Are you guys really spending 12 to 16 hours a week outside of this class? Oh, you're not. So if you're looking for ways to spend more time, you can take your worksheets and copy them back into a notebook. Okay, did you guys come to a consensus? What did you say? SP3. You all agree. Evan, say it. You think it's Jaylee? Evan?
We all disagreed on this side.
Tell me.
We're thinking SP2.
Okay, so we did not come to a consensus. My SP3 groups and my SP2 groups now need to battle it out. One of you groups is going to have to convince the other group.
Okay, so this is our reasoning. So there's 2 groups and then there's 2 pairs of lone pairs. So it might just be those 2 lone pairs, these SP and SP2, 3. And 2 groups of lone pairs contribute to that configuration is what we were thinking.
She's taking 4 electron regions. No, go ahead, Jaylee.
SP3 hybridized carbon, so would it benefit the molecule to conjugate the lone pair?
The molecule to, the carbon to oxygen's right is SP3. 4 electron regions, so the oxygen would spread those electrons out as much as possible, SP3. There's no intrinsic aromaticity because the carbon in that ring is not fully conjugated, so the ring can't be fully conjugated anyways. Okay, let's rebuttal.
Well, I guess I was kind of confused. But if that oxygen is engaging in pi bonding, it has to have a p orbital.
How do you know it's engaging in pi bonding?
The resonance.
Right. We did show a resonance form where it doesn't have 4 electron regions. So what made you assign hybridization off of one resonance form and not the other?
I was just going mostly based off of the lone pairs.
Sure.
Yeah, because I was like, that's what.
But in one of them, it only has 1 lone pair. Yeah? So how do you decide which one to count from?
Because I will conjugate, it can conjugate as well.
Nice. Well said. If it can conjugate, it will. I wonder who said that. Now, I really like that you guys brought up oxygen is not conjugating for the sake of the ring on the right, because that is never an aromatic ring. Beautiful. It's conjugating for the sake of the ring on the left. It's conjugating with the aromatic ring so that it can share its electrons with the pi system. Conjugation is this attractive thing for molecules. Okay, if it's sp2 very clearly in one resonance form, then I would argue it must be sp2 in all resonance forms, even if it has an sp3 kind of shape. Or not like shape like geometry, but shape like just the way that's drawn. I agree, this looks like an sp3 oxygen, but I also feel like this looks like an sp3 oxygen. And we know that this is sp2 for the sake of aromaticity, conjugation. Then this must also be sp2 if only for the sake of conjugation. Do you guys remember last week I was giving you resonance forms and I made you repeat after me? I said, these structures are not different, right? Something like that. I made you repeat it. And then I said, what's this hybridization? What's this hybridization? And you gave me different hybridizations. And I said, these molecules are not different. These are not different structures. They're different perspectives on the same molecule. If it can conjugate, it will. If it is conjugated, it has the same hybridization everywhere. It's a weird thing, but that is an sp2 oxygen. With that in mind, could you tell me what you think this bond angle is? We talked about this yesterday, I think, right? An empirical proof of hybridization, bond angles. 120. Despite looking like it should be a tetrahedral oxygen with 4 electron regions and being 109, we know that it's 120 because of this resonance form that proves that the bond must be 120. Great. Fun stuff, right? Okay, and then the oxygen versus the ketone. Which one is electron donating? Which one is electron withdrawing? The ether or the ketone? Which one plays what role? Perfect. That carbonyl pulls electrons out. The lone pair pushes electrons in. All right, Salsabil.
I'm sorry, I don't think I'm understanding why it's sp2 versus sp3.
Sure.
Do you mind explaining that one more time?
Can I turn it over to the class and see if somebody else can explain it? Why is it sp2?
Like, I understand, like, if it can conjugate, it will. I do understand that.
Yeah.
I'm sorry, I'm not seeing.
What does it mean to conjugate?
Doesn't it just mean if it can spread its electrons, it will?
If it can delocalize its electrons by putting them into a pi system that connects to several other atoms. Yeah, absolutely. If it can create an uninterrupted series of p orbitals, it will create an uninterrupted series of p orbitals. Do you know how many p orbitals an sp3 hybridized carbon has? Or an sp3 hybridized atom?
Doesn't it have 3 or 4?
No, no. How about the free atom? The theoretical atom on the periodic table has S and 3 P's, Px, Py, Pz. And then they start hybridizing. The S and 1 P hybridize to become 2 SPs. The S and 2 P's hybridize together to become 3 sp2s. The S and all 3 P's hybridize to become 4 sp3s. So an sp3 hybridized atom has how many p orbitals? Electron regions defined by the mathematical equation that looks like a propeller. How many?
Well, 0.
Because it's sp3 hybridized, what we're saying is S and P and P and P have all taken their mathematical equations, reconstituted their mathematical equations, and pumped out 4 identical orbitals that are 1/4 S and 3/4 P in nature. So the sp3 orbital is its own name. We could have called it something different. We could have called it the tetrahedral orbital versus the trigonal planar orbital versus the linear orbital. In fact, that maybe would have been a better name for them. I've been struggling to come up with better names for them, and it was just now that I thought of that. The tetrahedral orbital, the sp3 orbital, means that that atom has no p orbitals left. All of its p orbitals have been consumed, ground up, and spit out again in a new format. But the trigonal planar atom, the sp2 atom, has one of its remaining p orbitals that it can use to put a lone pair in, to conjugate, to be involved in resonance. The sp atom has 2 orbitals, 2 p orbitals, but they're perpendicular to each other. So if one is conjugated in a pi system, the other could be conjugated, but it would be in a perpendicular pi system. Since we know this oxygen is conjugated, we know there's a resonance form where it's sp2. Even before we saw this resonance form, we knew it could conjugate because a 3-atom system. If it can conjugate, it will. In order to conjugate, it has to have a p orbital, so it can't consume all of its p orbitals. It has to leave one unhybridized. Making sense?
I think so.
It's all about the orbitals. And just to remind you, here are those 3 p orbitals and s, px, py, pz. This is why when we say hybridize s and p to get sp orbitals, you get something linear, because you're only hybridizing along one axis, the x-axis, the y-axis, the z-axis. sp2 creates trigonal planar because you're now hybridizing a plane, the xy plane, the xz plane, the yz plane. And it's not until you hybridize all 4 of your atomic orbitals that an atom is able to distribute electron regions across 3 dimensions, tetrahedral. This looks like our traditional sp3. It is not your traditional sp3. This looks like your traditional sp3. It's not your traditional sp3. They have different justifications. This one is doing it for the sake of aromaticity. This one is doing it just to conjugate. I mean, overall, this is doing it to conjugate as well, but for better reason, for the sake of aromaticity. Okay. Ready? Ready to move on? We're going to get into section 16 on aromatic substitution reactions. And this conversation of electron withdrawing and electron donating groups will show up heavily in this section. So it's important to be able to think about conjugated groups pulling and pushing electrons. Aromatic substitution happens in 2 ways. All of these substitution reactions form by an addition step followed by an elimination step. So we see an aromatic ring. We see that aromatic ring go through an addition with either a positive charge or a negative charge on the intermediate. That has a lot of resonance forms, and then we see an elimination reaction. This is not SN1. This is not SN2. I personally hate those names to begin with because they have like taken the idea of being the only first order nucleophilic substitution, and I don't know, I don't like it very much. All addition reactions, all aromatic substitution reactions happen through this framework. An addition with a resonance stabilized intermediate followed by an elimination. The reason that addition isn't the final step is because this compound likes its aromaticity. It has an energetic preference to get back to being aromatic, but to swap out a group, it has to break aromaticity. And this is because we can't substitute on an sp2 carbon. We can, but it's not easy to. An SN2 backside attack would have to come from inside the ring, and there's physically not the space for that to happen. An SN1 substitution would have to create a positively charged carbon on an sp2 hybridized orbital. Not easy to do either. Okay, today we're going to talk about the nucleophilic aromatic substitution, which we name as NAS, or instead of SN1 or SN2, we call this SNAR. It's not a strong nucleophile doing a backside attack. It's not a weak nucleophile waiting for a carbocation to form and then doing an attack. This is an aromatic ring going through addition, then elimination. This is what we call SNAR. So you can call it SNAR, you can call it NAS. I like to call it NAS because it mirrors well with our other aromatic substitution, which is EAS, electrophilic aromatic substitution. The requirement here, an aryl halide is substituted by a strong oxygen or nitrogen nucleophile. So think of hydroxide, alkoxides, amide, alkylamides. Water is not a strong nucleophile. Ammonia is not a strong nucleophile. Ammonia is better than water, but all of these strong nucleophiles have negative charges, meaning that they readily form or they readily attack. Okay, I want you to also pay attention. This must happen with an aryl halide. Benzene itself will not go through NAS. Bromobenzene, chlorobenzene, they will go through NAS. Last thing about this, the nucleophile puts a negative charge in the ring, which means the ring acts as an electrophile. The ring is accepting electron density. And this negative charge is stabilized by conjugated groups that can pull electron density toward themselves. Electron withdrawing groups stabilize this negative charge and make it easier for the reaction to occur. So let's look at this first example. This is just generic. Actually, I could have made it more generic by just putting X instead of BR. But we're going to show nuke minus. We're not going to show a specific nucleophile for this one. We'll just say if it's a nucleophile. The nucleophile attacks the carbon where the partial positive is the greatest. It attacks the partial positive carbon bonded to the halogen, breaks the pi bond into the ring, and creates what is called a sigma complex. And this is what you guys are going to just be drawing arrows on. The sigma complex, as you can see, pushes the aromatic ring, or pushes that negative charge through the aromatic ring. So add your arrows to make those charges move across the aromatic ring as needed. How many resonance forms do you see? How many resonance forms do you see? 3. That's the minimum. This is what we call the sigma complex. I think the reason it's called the sigma complex is that all of the sigma bonds stay exactly in the same place. That's true of all resonance forms. So I'm not sure why they took that concept and applied it to this exactly. But the sigma complex, this is our sigma complex, always has 3 resonance forms minimum. Just by being the aromatic ring, it has 3 resonance forms.
What did you write down here? Stabilized by
EWG, which is electron withdrawing group, like the carbonyl that we saw on the last worksheet, or the nitro group that we saw on the last worksheet. What is this step? Is this addition or elimination? This step that we see. We've only shown one step. And then we've shown resonance forms. Resonance forms aren't a step necessarily. We've seen addition. How do we analyze addition? How do we know what addition is? Addition adds something across a pi bond. Addition consumes a pi bond, and we can see that we've broken a pi bond here. So that's our addition step. Now I want to reform aromaticity, so I need to do an elimination step. Addition plus elimination gives me my substitution. So my negative charge, my lone pair, reforms aromaticity and kicks off my leaving group. This is not SN2. The leaving group did not kick off at the same time that the nucleophile bonded. This is not SN1, where the leaving group leaves and then the nucleophile comes in. Jordan and Ju, you guys might remember in the spring, I gave an example of possible substitution mechanisms, and I said, what happens if the new bond forms while the old bond breaks? What happens if the old bond breaks while the new bond, and then the new bond forms? And I gave a third scenario, which was, what if the new bond forms and then the old bond breaks? And we said that was not a plausible substitution mechanism because it breaks the octet. Here's how we overcome that. Add the new group, then break off the old group, and take that charge that is put in there and put it through a resonance form. So it's not like it was an impossible idea. It's just that when we did it in the context of SN1 and SN2, it couldn't happen. But now with SNAR, it's exactly the order we do it in. Why did I kick off the BR bond? That's my leaving group. The nucleophile is substituting the bromine, the halogen. Okay, so I would like you guys to show the arrow pushing for the next one. Take chloro benzene and show me the resonance forms. Show me the arrows for the addition. Show me the arrows for the resonance forms. Show me how you get the final product. Keep in mind that Na that you see in NaOCH3 is just a positive charge, just a spectator. So you can redraw it as what is important, OCH3 minus. Good. Good catch. You're going to get real good at drawing hexagons, right? Not Evan. He's going to copy and paste them all semester. Perfect. Good start. Perfect. You guys are on it. Okay, while you're doing that, I'm going to put it up myself. Do you guys know what these brackets are? Yeah, they help to clarify what is resonance. Because anything in a bracket is not a different structure. It's just a different perspective on where those electrons are. Looking good. Nice. Great. Nice. I want you to think, if you were going to grade this, how many points would you make it out of? Perfect. Much better. I like that. You're missing one arrow here. The pi bond breaking. Perfect. And then you're missing the reaction arrow, the one that connects them. Great. How would you grade this? If I wanted to see the 2 steps and the 3 resonance forms, would you grade on the number of structures that you're expecting to see? Would that be part of the grade? Would you assign points to it so that you could just mark, this is how many structures I aim to see, and if I see less or more, then it comes out of these points. Then assign points for arrows? Because in my opinion, if you can show me all of the intermediates of a mechanism, that's half the job. Drawing the structures is part of knowing how the reaction proceeds. Drawing the arrows is part of knowing how the intermediates connect to each other. So those are the 2 tasks that I see. What I've tried to do is assign points based on the number of steps. And then I split those points between the structures drawn and the arrows drawn. But I actually noticed on the Unit 1 test, I gave you a 2-step mechanism and I gave it out of 3 points. And I worried that might have scared some of you into thinking it needed to be 3 steps and not 2 steps. But for that one, I was looking for arrows on the first structure to make the intermediate, the structure of the intermediate, and then the arrows on the intermediate to get to the last structure. So I think if I were to do that here, I would say 1, 2, 3, 4, 5, 6, 7. This would be a 7-point problem, despite being 3 steps. So it's like 1 more than twice as many. It's 3 steps in it, and I'm doubling the number of points and then adding 1. I don't know the best way. I'm still trying to figure it out. I thought I had the best way figured out. I think I'm still trying to figure it out. One of the most common mistakes that I see in these mechanisms is skipping too many atoms. Remember your 3-atom system when you do a resonance form. The electrons at this negative charge can only go forward or backwards. Those electrons need to stay with that carbon. So they go forward to this carbon, which means this carbon breaks its octet. So these electrons need to break. And they can only go to one of those 2 carbons holding the pi bond. So it obviously has to go here. So count your system. Pay attention to your 3-atom system. Make sure you're not going too far. Okay, so far so good. Now let's make it more complicated. When we have these electron withdrawing groups, a group that can take electrons out of the system, take this negative charge, get it off of a carbon, and put it onto something more electronegative, something like a nitrogen or an oxygen. Notice where the negative charge ends up. The negative charge ends up ortho to the halide and para to the halide. So I need my conjugated electron withdrawing group to also be ortho or para to the halide. And we're going to see in this one, I'm skipping the 3 resonance forms that are minor. I don't show you any resonance forms where carbon holds the negative charge. Why? Because when negative charge is held on oxygen or nitrogen, that's a better resonance form. And that's how I'm going to grade these. I'm going to look for only the major resonance form. That's the one that is more significant to me. I did make a mistake here. 2 mistakes. I should have drawn out those groups at each step because I wanted you to add arrows here. So you're going to need to modify those groups and draw them out so you can show bond breakings. I also drew the NH2 as nuke in one of the steps. That should still just be NH2. The major resonance forms. Only occur at ortho-para substituted electron withdrawing groups. Do you notice one of the groups doesn't ever involve in the resonance structure? That was great English. One of those groups is not involved in the resonance structure, and it's the sulfonyl group, because the sulfonyl group is meta to the halide. The sulfonyl group is never in a position where that negative charge hangs out, so the sulfonyl group can't help pull electron density out. All right, once again, I'm going to stick with the drawing that I have, but I want you to remember that you can redraw these structures, the resonance form of the aromatic ring, however you'd like. All right, I'm taking amide, NH2 minus, and amide will attack at the bromine's carbon. Can you tell me why it doesn't attack any of the other carbons? There's a nitro, there's a nitrile, there's a sulfonyl. The halide is the leaving group. And that's why it's attacking there. I'm going to show the major resonance form. So rather than just kicking off the negative charge to sit on the carbon, that is not a major resonance form. I'm going to move this pi bond into the nitrile and break the triple bond of the nitrile. This is why I need you guys to show the CN triple bond. You can't abbreviate it as CN because you need to show the triple bond breaking. True or false, it would be wrong of you to draw this resonance form first, like we did in the last problem, and then show this resonance form moving the negative charge up to the nitrogen. True or false? It would be wrong to show this and then this if you were doing this for a graded problem. I'm showing you a resonance structure here where the negative charge is held on the carbons. I'm skipping that resonance form. Instead of showing it held on the carbon and then moving into the nitrogen, I'm just skipping over that carbon and going straight to the nitrogen. I'm skipping this minor form where carbon holds the negative charge, and I'm showing straight to the major form. Would it be wrong to draw this first and then have it transition to this? No, it's just more steps than I'm going to grade on. I'm going to grade for the major resonance form. But it is not wrong to have minor resonance forms in there. You okay with that? If it helps to do one resonance movement at a time, then do one resonance form at a time. Now, I want to go from this resonance form to my next resonance form. Notice my next is also a major resonance form because oxygen holds the negative charge. So to get there, my nitrogen gives up the electrons, reforms the triple bond. My carbon gives the electrons back into the ring. Remember, this nitrile withdrew electrons. Now the electrons are going to get withdrawn into the nitro group. I made a mistake, and I didn't draw out my nitro group. And I need to, because I need to show that NO double bond breaking. If I don't show the NO double bond, I can't show it breaking, and I need that bond to break. The pi bond in the ring gets pulled out to the nitrogen, and the pi bond of NO breaks to the oxygen. See all those arrows? That's a lot of arrows. There are so many resonance forms in between. There's a resonance form where this carbon in the ring holds the negative charge. There's a resonance form where this carbon in the ring holds the negative charge. And I'm just skipping over them. Why? I would draw a million structures, and I'd be drawing minor resonance forms. I'd be drawing forms where carbon is holding the negative charge. Now I'm done. Oh, I forgot my sulfonyl. By the way, this is what your sulfonyl looks like. And no matter how you try, you will not be able to legally get electrons from this nitro group into that sulfonyl group. And we can try. Negative charge of oxygen reforms the pi bond. The CN double bond pushes back into the ring. There's no way for me to get those electrons into this sulfonyl group, so the only other place to go is the last ortho carbon. But I don't really care to show a minor resonance form, so I'm just going to move directly to the elimination step. true or false, that is the only resonance form that can be used to show the elimination step. The elimination has to be shown from this resonance form specifically. No. Why would it? This resonance form doesn't even exist. Why would this be the only way elimination can occur? This is just one way that we can show into the elimination step. It's not the only way. What do you prefer? And I don't mean that patronizing. I need you to do some self-reflection and decide, because when you do your homework and you show your written work and you show an NAS mechanism, you need to decide, will you show every resonance form, including major and minor, or will you look for where the major forms will be and just draw directly to them? This is what I like to do. I'm not going to take off points if you draw legal, correct resonance forms in between that are just minor. But what do you prefer? Do you have an intuition yet?
Can I ask a question?
Sure.
The ones on the right, though, those are all major, like those three, correct? These ones.
Yeah, technically these are all major resonance forms because there's no electron withdrawing group. So there's no better place to put them. But the same forms that exist with these, so there's 5 total forms. Those same forms where carbon's holding them, they become the 3 minor forms. These are the 2 major resonance forms. All right, well, you have 2 problems. One of them is to show an NAS on a para-sulfonyl substituted aryl halide with hydroxide. The next is to show substitution with an aldehyde and a ketone substituent, and I want you to decide which halide substitutes. Why don't we start with the one on top? How many major resonance forms do you suspect will be in here? Three major resonance forms, which would mean only the minimum resonance forms, so no electron withdrawing groups involved. I disagree, because that sulfonyl is para to the leaving group, and that sulfonyl can pull electrons out. It has a conjugated pi bond. I think you're going to see one major resonance form. You could show all 4, the 3 basic ones of the sigma complex plus the electron withdrawing group, but only one of them will be major.
So how come we showed it in there, like this sulfonyl group drawn out, if it doesn't really do anything, at least in
I wanted you to see its structure. I wanted you to know how it's bonded. Is this sulfonyl group ortho or para to the leaving group? No.
Pairs across.
Para is across. Ortho is,
Oh, in this case, it's ortho, like in this one, but right there, it's technically para, right?
to the leaving group. Look at the starting material of the product, maybe. Ortho is adjacent. Meta is 1, 3. Para is opposite.
Oh, so
It's meta,
There you go.
which is why it's not involved in the resonance forms. It will only be involved in the resonance forms if it's ortho or para, because the sigma complex puts the negative charges, ortho and para, to the leaving group. So how would I grade this? 2 steps, 1 resonance form. I would have graded this as 3 steps with 2 resonance forms, but this one, fewer steps because there's fewer resonance forms. Good start. Can I share? Jaylee's drawn out all of the sigma complex intermediates, and you are always welcome to do that forever, or even just until you know how repetitive they are and where they're always going to show up. Great work. Jordan's skipped right to the major resonance form, although you did draw the sulfonyl wrong.
Oh.
Perfect. And then again, yep. Your arrows are kind of looping the whole ring.
Yeah.
But remember, to do anything in the sulfonyl group, you're going to need the sulfonyl group drawn out. There you go, Evan. Same thing with you, Mimi. If you want to show the sulfonyl group taking electrons, you'll have to show a bond breaking inside the sulfonyl, which means you'll have to draw out the sulfonyl. That was my bad on not setting you up for success on that in this worksheet. Now, if you're done with that mechanism, think about the next one. Where will the nucleophile attack?
Matter. I drew it this way,
Yep.
and it just technically is gonna be not the same. Like it is, but
It
just
is.
flipped. So is that okay?
Absolutely.
Okay.
Jordan's question is, what if my resonance form of the ring doesn't have the pi bonds in the right spot? Does my resonance form here even agree with the resonance form I put up there?
I mean, you didn't even.
Because it doesn't matter. Yep. So if I draw the pi bonds in one orientation, you just draw them in whatever orientation you want. So think about that next mechanism. What are you going to see with the two halogens? Can I take a look at your first step? Right. So you're expanding sulfur's octet too much. First of all, this is net negative, which means that this needs to be negative. Where would that negative charge be? Well, I mean, it did move, but it didn't get isolated there. It also just kept going. Which atom did you give additional electrons to?
On this one,
Mm-hmm.
to the carbon?
No. All your carbons kept the same amount of electrons. You gave more electrons to the sulfur.
Okay.
So the sulfur would technically have a negative charge, but really it won't. What you did in the first step, I would draw the sulfonyl there and show this bond breaking here. You see what I'm saying? The sulfur itself won't take the electrons. So when these electrons push in, then the SO double bond breaks. Perfect. Good work, Evan. Good start.
So,
But the sulfur won't really want to just keep them.
Right.
Instead, oxygen would pull on them better. So if we added one more arrow,
So this wouldn't be double pumped.
right, right.
Oh, so you're saying it would be like.
Yes, that's exactly what I'm saying. Good. Great, Jaylee. Here, you've got those two arrows, which actually are just one. This double bond moves, to this region.
Okay.
Actually, can you go back just a couple changes? Do you see how this arrow is telling you to start from the sigma electrons, the single bond? There's no other electrons there, so you must be saying the single bond goes just to this carbon, and you're saying the pi bond goes just to this carbon. What we actually want, based on your structure, is we want this pi bond to go to this region, which is going to overwhelm this carbon, so its pi bond also moves.
Okay.
So just one arrow. Oh, I went the wrong way. Redo, redo, redo. Just one arrow from here, but not to this carbon, from here to this bonding area. Great. All right, I'm going to draw in my version. But alternative versions to this would include all of the sigma complex. And that's where I find you're just going to kill a lot of time drawing non-major resonance forms. But I do think there's some value to drawing all of those sigma complexes until you recognize the pattern that they move with. Once you know the pattern, then it's easier to identify why you can skip over it and get to your product faster. See, now I've already drawn a lot more than I needed to, so I'm just going to skip to the end because I'm allowed to. All the rest of these are just minor resonance forms. Sound good? Practice doing all of them if you want to. Evan, I saw you did it. Did that feel helpful to be able to track where the negative charge moved?
Yeah.
Jaylee, same for you?
It'll be easier to just go to a major resonance form.
That's my goal. Over time, you'll see what all of the individual steps are needed to be. Okay, we'll finish this and do some resonance or some synthesis on Tuesday, and then we're going to spend the rest of the week on EAS and synthesis. Okay, have a good weekend. You've got one homework problem, one written work problem that you can get started on too, the NAS mechanism.